If you are 30 years old, you can likely recall specific moments from when you were 10. But if you are 20, you almost certainly cannot remember being 1. The rate at which we lose these early memories doesn't follow the standard logic of time. It isn't a total loss of data, though. While the events are gone, the skills remain. You don't forget how to walk or how to speak the language you learned as a toddler. Those systems are permanently integrated. We specifically lose episodic memories, the chronological record of life events and their sensory details. The brain keeps the software for movement and speech, but deletes the personal logs. This creates a question of efficiency. If an infant brain has the processing power to master human language and complex motor skills, why does it fail to maintain a record of its own experiences? This universal blind spot, known as childhood amnesia, reflects how the human brain prioritizes and organizes data as it matures. There is a chronological twist to this forgetting. Toddlers actually can remember events from their infancy. However, around age 8 or 9, the brain begins a process that retroactively clears those early files. Between 4 and 24 months of age, an infant brain is exposed to a continuous stream of sensory input. Every texture, sound, and face is a new data point requiring attention. For information to move into long-term storage, the brain must first recognize it as valuable. This encoding process acts as a gatekeeper for what is worth keeping. But an infant lacks the cognitive context to grade the importance of an event. They cannot distinguish between a significant family milestone and a routine afternoon, making it difficult for the brain to decide what to commit to long-term memory. Without this filter, early episodic memories are encoded weakly. They are placed on an unstable foundation, making them vulnerable to the biological changes that follow. The hardware for this process is the hippocampus. This region is responsible for the formation and storage of our life's episodic events. In early childhood, the hippocampus is a construction site, rapidly producing a high volume of new cells, or neurons, as the brain expands. A research team in Toronto investigated whether this rapid growth of new cells was actually the cause of memory loss. They found that when they forced adult mice to produce more neurons, the mice became forgetful. The surge of new cells in the adults effectively induced the same amnesia seen in humans. When they reversed the experiment, slowing down cell growth in young mice, those mice were able to retain their early memories much longer than usual. The physical mechanism works like this. As thousands of new neurons push into the hippocampus, they shuffle and disconnect the existing memory pathways. This biological rewiring breaks the fragile links to those weakly encoded files from infancy. The old pathways are not just obscured, they are often completely overwritten. The physical expansion of the brain requires a reorganization that inherently clears the data collected during its earliest stages. This suggests that childhood amnesia is a structural feature of maturation, not a biological failure. It is a trade-off. While slowing down cell growth might preserve your first birthday, the brain requires those new neurons to develop the complex cognitive abilities needed for adulthood. Researchers are now looking at how this same cellular growth impacts other areas of the brain, including the amygdala and prefrontal cortex, to see if they follow the same pattern of loss. Losing those first few years of personal history is the cost of building a more capable brain. The processing power used during infancy wasn't intended for long-term archival. It was used as the scaffolding to construct your current mental abilities. You cannot remember being a baby because your brain sacrificed the record of its own beginnings to build the person you are today.